Thanks for the invitation, and it's a great pleasure to be here to talk about our recent work on quantum simulation using spin models in trapped ions, and full aspect of cosmology and high energy physics. It's a great pleasure to be here, and I learned a lot about theories. Well, actually, to be honest, I learned a lot of things about what I don't know about black holes and AES-CFTs. Here's a okay. I went too fast. So here's a brief outline about my talk today. So I will first talk about the spin system. The spin system we have used trapped ions. I guess maybe some of the experts are already familiar with our system from Chris's talk or somebody another's talk from our group. But try to get everybody on the same board. I'm going to be briefly tell you about how we actually engineer such a spin model, Eisen type spin model with tunable, with amplitude and a range tunable interaction between spins. After that, I will briefly tell you about what sort of interesting physics we can study and we have studied. But I'll mostly focus on the aspect that relates to cosmology and high energy physics, which is the thermal double state, the preparation of the thermal double state using quantum algorithms, quantum approximation optimization algorithm. And at the same time, also talk about the quantum particle confinement dynamics, our spin system, which relates to the confinement of quarks in high energy physics. So, like I said, we're going to use spin systems to do quantum simulation. What is the physical spin in our system? In Chris' lab, we use ytterbium-71 ions as our physical spins. Basically, we encode the spins in the S half state of the ytterbium ions. We call this the clock state, where it's from 0, 0 to 1, 1 transition, where its first order is sensitive to magnetic fluctuation or something like that. And since it's not sensitive to any magnetic field noise in our system, we have very long current lifetime, like 10 minutes. It's pretty good qubit to do quantum computation or quantum simulation. Like all kinds of ion experiments, trapped ion experiments, we do trap our ions using ARF traps, and also we do laser cooling and trapping and cool them to the very ground state. After that, we can prepare the initialize the spin state by just simply do optical pumping, which we just shine some laser beam across this transition, so that would decay to the very ground state or the spin down state in our system. We can have very high preparation fidelity. After that, if you say I don't want the spin to be in this state, I want it to be in some superposition state or even the up state. From there we can just shine some microwave, do a spin flip to the spin up state, or you put them in a superposition state. We can also even do it with just optical pulses, with Raman pulses as well. So after we prepare these things, you may be curious how we're going to measure the spins. In our system, we just collect fluorescence of the spins to say whether it's in the up state or the down state. Basically, what we do is that we shine a beam across this transition. If the spin is in the up state, it will scatter photons. It will collect fluorescence. It will be bright on our camera. And if the atom's in the down spin, right? It's this is about 12.6 gigahertz attuned, which is 60 times of the natural alignment of this transition. So it's very far to the rarely scatter any photons. As a result, it's dark on our camera. So here I'm just showing an example image of how the spin looks like when we prepare them in the antiferromagnetic ground state. So stagger state spin up, spin down. With the bright means spin up state, and the dark side means spin down state. So just to entertain you a little bit, here is a movie about how we actually load our ions, and you see as time goes, ions get more and more and more. So to load the ions, we actually lower our trap, so we have a bigger trap volume. It doesn't really trap the ions into a chain. It's kind of like a self-crystallized structure. And after we load enough ions, there's some counting of the ion numbers here. As we load enough ions, we just increase the trap depth so that the ions just self-organize into a nice long chain. So So far these ions, right? This spinner, this ion spinners looks very similar just to a neutral atom spinner, like Malika mentioned yesterday. But there is, except the fact they're charged. Actually, the fact they're charged has a very important consequence in this case. Since they're charged, they have strong Coulomb interaction between each other. As a result, the motion of the ions, individual ions, actually couple to the motions of the other ions. So here I'm just showing you, some examples of the motional modes of the ions, because the ions because they all have the same sign of the charge. So the Coulomb interaction is actually repulsive. So as a result, the center mass motion, which has the longest wavelengths, has actually higher frequency compared to the shorter wavelength vibrations. The shorter wavelength vibrations actually, the zigzag mode, where actually, the ions separate from each other and have lower Coulomb interaction, and it's actually lower mode. We also have much lower axial modes, simply because this direction is confined by simply static electric force. It's much weaker than the radial direction. So now it turns out, we can actually use these vibration modes to actually engineer as a bridge to engineer interaction between spins. So here, just give you a simple impression about how many these modes we have in our real system. So here I'm showing you a spectroscopy of the motional modes. We have both the X and Y modes, basically just the transverse modes. The axial modes will be far away up there. We never use it because it's so slow. And these modes are actually fast to do the quantum gates or do simulations. So now with these modes, here I'm trying to show you in two picture how we can actually use these motion modes to engineer spin-spin interactions. So to do that, we actually need to shine some Raman beams. So basically, you can imagine that we just have two beams come from the opposite side of the ions, and then they come in here. What happens is if one ion here, one ion scatter, absorb one photon from the one beam and scatter into another beam. As a result, these ions will get a momentum kick, so let's say delta K. Once they're kicked, because the motion is all coupled, right? Once they kick, the whole chain would start to move. When the ions start to move, it will change how the ions will perceive the laser fields. Consequently, it will change how the spin flips as they start to move. So in the real experiment, the configuration is a bit more complicated. We have to sort of address both the blue side and the red side band. The blue side band means that what happens that when you flip a spin, you actually destroy or eliminate a phonon from the vibration modes. Look at some vibration modes here. Well, for the blue side band, when you flip a spin, you actually create a phonon into the system. So here is there's some parameters here. So omega is just simply the Raman frequency, or two-photon Raman frequency. The omega HF is just a simple the hyperfine splitting, which is 12.6 gigahertz in our system, and these are just small detunities away from the red side band and blue side band. So in our experiment, we actually shine both of the beams together. So we have a blue side band addressing and we have a red side band addressing and the blue side band addressing. As a result, if you sum these two terms together, you would get some coupling between the spin and the motional modes, right? As you can see here, this I is the index and the spin number. So 1 to 3 or as many spins you want. You can all couple to kind of similar modes, AM, for example, a similar set of modes. As a result, sort of like these spins can couple to each other using the bridge of the motional modes. All right? If we do some tricks in mathematics, eliminate some of the fast rotating terms, we can sort of have a term of just spin interaction. Trace out the emotional degree of freedom. Only have the spin as spin coupling. It's different sides. So what is interesting here is that we can not only we can tune the amplitude, for example, changing the Raman frequency here or changing the angle between the two beams. And, depends on how much that depends. That gives how much momentum kick you get from the Raman beams. we can change the sign of this thing. We can change it to an antiferromagnetic interaction or a ferromagnetic interaction. More importantly, we can also sort of like change the range of this thing. Just to another extra thing, if we want to add a transverse field, we just need to shine some beam on the carrier, which does not create any motion. Right? It only goes from one spin to another spin, does not create any motion, and just act as a B field, very similar to Malika's configuration. And also, these B's are the motional modes. If we write down the normal modes of these different modes, and we do a more careful calculation, we would find out our interaction is sort of in the form of a G naught divided by the distance between two ions. You can say, sorry.
Maybe you can just say that a little more slowly. So if I wanted to dial some particular interaction between pairs of atoms that I came up with, then I have to choose I can always choose some B's that will accomplish this.
Yes, exactly. So for different sizes of chains, you would want to choose to address different modes. For example, if you want just to address these two ions separated by some distance r, you need to do very careful control that you only excite certain set of modes so that you only have motions like this, right? But for in general, you can just apply a Raman beam. They can have all different sort of color.
All of that is driven by this Raman.
Yes.
So you mean you have an ability of tuning to a particular shape of mode that only affects one?
Yes, we have to do a very careful shaping of the pulse we actually apply to the atoms. So that's actually how we make pretty good quantum gates out of these. We just choose to flip two. We can just, for example, apply a two-gate operation on two of the ions that are actually separated by exciting some of the modes. And then it'd be tricky that we have to also decide it when it's entangled. When the spin entangled, we have to actually go back to the zero position when the ion didn't move at all. So we disentangle the spin and the motion in the end. So we only have spin-spin color. Just to give you a general, you just need to remember this. The takeaway is just you have some spin-spin coupling, and with its amplitude tunable by just simply changing how much power you apply for the Raman beams, or what set of motion modes you want to excite. Basically, just choose a different tuning. And it also depends on log r to the alpha. We can tune this alpha to from 0 to 3 sort of thing. 0 is basically just constant interaction, very long range, just like Malika's case, where you have global spin-spin coupling. While 3 is sort of lower, short range. You can sort of consider nearest neighbor or next nearest neighbor coupling. Okay, so I sort of swept a lot of the details of this configuration into the rack, under the rack. But if you're interested, we have I cited this paper here. Just give you a few more seconds if you might write it down. If you are interested, feel free to check this paper to have more detailed information over that. So now I have sort of all the components to make this
question. So is it you can already achieve some 2 qubit gates and do universal quantum computation?
Yes, just to give you a rough idea, so in Chris's lab we have a Eureka system, which is black box. On a computer, it has 21 qubits. We can do 99.9% fidelity 1 qubit gate and 97.7% XX 2 qubit gates with 20 ions. Feel free to check it out. We also have another machine with less qubits, which has a paper on archive that's benchmarking the quantum computer. So sadly, we'll find that one has also demonstrated similar fidelity we can do. So
also in terms of simulating many-body system, how does it, for example, compare to Malika's cold atom system?
Oh, that's an interesting question. So I guess from my perspective, Malika's system is not ready yet, but it's close. But we have been doing this for years. It's already there. And to compare with Malika's system, we have they have this cavity and atom coupling, right? So they can do a very long range interaction, but the range of the interaction is actually very hard to tune. So basically, when you have that, it's global coupling. For our case, is that we can just tune the
Pause.
tune the pulse so that we can tune the interaction. So tune the for example the Rabi frequency or the tuning. We can tune the range of the interaction. We can also do careful pulse engineering. Only couple for example particular two ions and do qubit gates, something like that.
I guess if you don't mind, I realize I'm the only person here from Monica's previous group, so maybe I can add a little bit. I think the two experiments are just in two different regimes. So here, you guys are, well, it sounds like you're engineered very nicely to do exactly, 2 qubit gates, doing this more discrete style quantum computation.
Oh yeah, so we're adjusting each qubit, but I think in Monica's is
right, exactly. Monica's is
system.
in a different regime where there are many, we have 10,000 atoms instead of 20 qubits that we're trying to do exact gates on. And it's we're more interested in, or she is more interested in, continuous time, like mini body simulation type things. So yeah, similar capabilities, but kind of different regimes of yeah.
I hope I didn't say anything bad.
No. Everything was
Yes, another fact is we can really just know what's the state of each of the qubit. While in Malika's experiment, I think you're interested more in the global measurements, the whole. What's the status of the whole spin system instead?
Right. Well, so in Monica's experiment, she also has localized imaging. It's state-sensitive localized imaging, but it's not single qubit.
Is the time scale very different? This is say 1 kilohertz.
I think that the CAP experiment is much higher.
Yeah, from what I learned yesterday.
Higher rate,
higher.
faster.
So from what I learned yesterday from Malika's lab, I skipped the last talk, but I learned something from Malika's lab. We can do up to 10 kilohertz-ish.
Yeah.
J. Yeah. We do up to 1 kilohertz. It depends. Actually, we can do faster with less ions, but when we have more ions, we can do a little bit slowly.
I think it's limited mostly by the rate of the modes, right? It's limited by the
yes, vibrational modes.
Exactly.
Yeah. So we have to use the motion. The motion normally is, in our case, is from accuracy, so that's sort of set ultimate limit to that.
What's the main decoherence mechanism?
Oh, in this, the main decoherence is from the lasers. It's how well you can control your laser pulses. So there's no. I would say, according to Chris, there's no fundamental limit to this because our qubit is so good. And it's much nicer than the Drussel junctions, right? Because our qubit is identical.
And the qubits are not coupled to anything else.
Yes, yeah. So we have a co-interaction, but this co-interaction does not couple the spin directly. It only couples the spin when we shine laser beams. So yes, it's pretty nice system. The only limitation is just how well we can control our technical details. Right. Hopefully you enjoyed our system. Okay, now I'm going to switch gear a little bit, talk about sort of physics we can do in your system. Okay, before that, I forgot, I have this slide. So for that, I will just show you where those spin models are actually in our real life lab. So here, that's the thing I was mentioned. Your question, that was the Eureka system, which is a 21 qubit quantum computer. It's you can put a screen here, a keyboard as a computer. You can just program it and run some algorithms. Here it's sort of everything runs more in a circuit manner. You apply 1 qubit gate and 2 qubit gates, and sort of do simulations here, in a digital manner, let's say. We have another 2 systems. We call it the analog simulator. We just we have a chain of ions. We apply some Hamiltonian, and then we look at the dynamics, how things evolve, and what's the state of the ions, right? And we have 2 different systems. One we call the cryo system, which actually we run at ultra low temperature, as a 4 Kelvin-ish. So at that temperature, okay, you may be curious why we run at that temperature. So the reason is that we can get the vacuum done by a factor 10 to 100. So that's much better vacuum. So you have less background collision with the with background gases. So we can hold the ions for a very long time. For example, we can have a 121 ion chain for a few hours.
You're getting the vacuum done
by a factor of 10 or 100 better.
Or 10 or 100.
10 to 100. It depends on what temperature, right?
But not 10 to 100.
No, not 10 to 100.
That's very, very.
Yeah, apologize for that. Good catch. Right. So But for warm QSIM, this is a more recent generation, but we still keep this system running. In that system, we can at most have 53 ions, but we lost that like after a few minutes just because of background collisions. But anyway, so these system hosts all these spin models, and based on this, we can do some interesting physics. So we have actually, since you were asking, how long have we been working on this? These machines have been working for a very long time. We have been doing a lot of interesting physics. For example, we can study the equilibrium physics, see the ferromagnetic, antiferromagnetic phase transitions, look at their ground states. We can also detect the non-equilibrium dynamics, observe the, so going to be interesting, the observation of the time crystal, which is a collaboration with Norman and back in Berkeley. We'll also be able to observe another interesting dynamics and dynamical phase transition sort of thing like that. But in this talk, I'll mostly focus on the aspect that relates to cosmology and high energy, which will be the quantum scrambling and Zimmer double state preparations, and also the simulation of quasi-particle confinement. So in the next talk, I'll mostly focus on this topic first, the thermal preparation of the thermal double state, and sort of steal this from Hugo's slides. I don't really know much about this, but just for entertainment. This work has mostly been done in circuit simulator. But before I directly do this, I also want to mention the quantum scrambling first. So this is another thing I learned yesterday from Sherry's talk. I don't know what scrambling actually means. He's not here. But okay. Basically, from our naive understanding, scrambling is just meaning a very fast and complete diffusion of information across the whole system. From the perspective of black hole physics, I thought our naive understanding is that if you have a black hole here, and black hole for maximal scrambling of information. If Alice somehow threw some qubits into the black hole, and the black hole scrambles information across, diffuses information across the whole black hole, and there's some, if Bob is somewhere else looking at the Hawking radiation from the black hole, you might be able to just reconstruct the state what Alice sent you. Well, given that you have maximum scrambling. So how do we actually do this in our system? So we came up with some protocol, some circuit diagram to actually mimic black holes. So we use this kind of a random unitary matrix or random unitary evolution of the system to actually to mimic the scrambling of the black hole. Depends on how strong this random matrix, how strong we apply this random matrix or random unitary evolution, we can put a different amount of scrambling into the system. To test that, one can just mirror the OTOC, right? OTOC, all-time ordered correlator. How you see when this thing decays, then you have scrambling. But in a real system, right, OTOC also decays because of decoherence. We have to tell the difference between real scrambling as well as the decoherence. So what we do here is actually we do more complicated. So Alice threw some qubits into the black hole, and Bob wants to reconstruct information. He has to do more things. He needs more and more quantum memories. For example, he needs those EPR pairs, right? He has to throw two of his qubits into the same black hole where Alice tossed the hers. And in the meanwhile, he also didn't know how does the black hole actually scramble the information and apply some conjugate Hamiltonian to his own qubits he didn't throw into the black hole as well. After that, he did some projection measurements. These projection measurements actually give you the all-time ordered correlators. Right? We would see the decay, it looks like there's some scrambling, right? But how do you verify it's scrambling or decoherence from his own circuit? Basically, the scrambling also, another consequence of the scrambling is also it teleports. If there is scrambling, it would teleport the state put by Alice here to the qubit that Bob puts in here. So here's a sort of like a circuit diagram, how we're going to mimic this black hole in this random circuit. Here's just a quick snapshot of the data from the paper where we mirror the projection rate to the original Bell states, which basically tells you how fast information was diffused across the system. And we see it decays. And a lot of people actually measure the same decay as well, but it's hard to verify it's from decoherence or scrambling. But meanwhile, we can also measure the teleportation fidelity, right? If the teleportation is successful, that means these decays are actually from scrambling instead of decoherence. So this is one of the collaboration with Norman, and this kind of this kind of a simulation or experiment actually have us excited. So we can do more into the aspect of this to study cosmology physics as well. So the next thing we did was we tried to sort of prepare a thermal double state. See if we can do that as well. Sorry, I apologize for the resolution. It was better on my computer. So I can motivate this thermal double state in a slightly different way. From what I learned in AMO, I thought if you have a mixed state, with a thermal mixed state, if you want to treat this state quantum mechanic with a pure state, the simple thing you can do is just duplicate the same state. You don't have to exactly the same, but at least have the same degree of freedom. And sort of like you can write the thermal double state as the highly entangled state. Yeah, it's good that everybody knows thermal double state already. And if you trace, if you do a local measurements on system A, you automatically trace out the degree of freedom on system B. As a result, all the observable looks like thermal. Although this state is pure. Obviously, this has interesting implications in eternal black holes, like Hugo talked about, and also Brian. Also, like somebody also interested in Hawking radiations. Where in Hawking radiation there's some virtual fluctuation on the event horizon that break into two pairs of particles. One falls in, another flies out. You can actually observe it, but all the observation would be thermal. However, the state itself initially at the event horizon is still a pure state, thermal double. So can be described by the thermal double field state. Also similar to our radiation, which is an observation from an accelerating observer. Okay, it's out of order. I apologize. So there are also interesting connections to the kinetic matter system, where these thermal double field states actually connect to the tumble squeezing vacuum state as well. For example, in the early paper on super radiance, where in Wolfgang Keller's experiment, where you shine a beam to VEC, you would see a simultaneous scatter of light and atom at the same time. So it's a tumble squeeze state of atom and light. There's also has been this coherent spin collision experiments like Malika's experiment. This is the Localized experiment, where the spin collision simultaneously produces a spin up and spin down state, and they can actually use this to improve the quantum sensing. More recently, we have also the pair emission of collective matter waves, where you simultaneously generate a pair of jets out of a VEC by multiple interactions. Also, in Malika's system, you can also do similar experiments to generate sort of spin double squeeze state. But for a long time, people in kinetic matter always just consider this is tumble squeezing in vacuum, but actually it also has connection with the thermal double state. So, given all the system, they're all kind of employ a pairwise generation where you have to generate something in A and B simultaneously. But in our system, we try to do a slightly different way, because we have a quantum computer. In principle, we can do it computer-wise instead of just apply some Hamiltonian. So what we're going to try to do here is try to generate this thermal double state using a quantum approximation optimization algorithm. And to be honest, it's not really a quantum algorithm, right? We can't eliminate this. It's not a quantum algorithm. It's an optimization algorithm involves a quantum system. So let me frame the question a little bit more clearly. So let's say we have a state we want to prepare. It's an interesting state we want to prepare. How do you do that? Normally, we can encode this state to the ground state of a particular Hamiltonian. We call it cost Hamiltonian, right? So you just want to get to the ground state of that cost Hamiltonian. Normally, what you can do is that you start with some Hamiltonian with a ground state that's easier to prepare. You start right there with the ground state easier to prepare, phi 0, and then you just diametrically, lower the other part of the Hamiltonian which you're not interested in. Here we call it mixed Hamiltonian. If it's not interest, if you just diametrically lower it, there seems to be a trace, like the time trace you have to follow from here to here, so that you from one ground state you end up with another ground state without create some excitations, right? So normally this is kind of a time consuming. It takes a longer time because you have to do it diabatically, and it's particularly bad for a system that has limited coherence lifetime, for example. But instead we wanted to try things differently. Instead of going along this trace diabatically, we just try to jump it around. By just alternating to evolve the system with these Hamiltonians by terms. We just apply some constant Hamiltonian first, and then we mix a little bit, and then we apply it for many layers. And each of the layer has some parameter beta and gamma to just determine how strongly we apply this Hamiltonian or how long we apply this Hamiltonian. So we can, in that way, we can just jump around in this path without following this diabatic. So we sort of demonstrated this kind of a QA/OA in both the circuit and analog machine. But here I just mention the circuit machine with like I believe 7 qubits. Basically, like I mentioned earlier, we just take turns to apply these Hamiltonians with different parameters and apply it for different layers, right? And we call this Hamiltonian as the cost Hamiltonian. This is the mixed Hamiltonian. So basically, this is how these schematic circuits break down into different qubit gates. We have many XX2 qubit gates, some single qubit rotation gates. This is just for one layer. So what we see is that we can actually successfully prepare the ground state of a Hamiltonian. Here we are trying to prepare a ground state at the critical point of this IC model with G equals 0. So basically, that's where from a ferromagnetic to paramagnetic phase transition happens. We can see that with only one layer, just apply one layer of this by adjusting these parameters, we can already do a very good job by preparing the ground state of this Hamiltonian. We can also do multiple layers. And also, important thing is that it doesn't really matter which state you start. Right? In a diabatic regime, you have to start with the ground state of the particular Hamiltonian you started. But in this case, you can start with whatever Hamiltonian. You can start with you can start with an initial state that is close to the ground state, right? Basically it doesn't really change much; it stays there. Or you start with the state that is far from the ground state, and after some iterations of optimization, you will get back to the ground state.
Great.
Sorry, can you explain a little more how this works? You're doing imaginary time evolution in this sort of flow K fashion, but you're getting to the ground state?
Sorry, okay, let me explain more. So basically what we do here, it's not flow K. Basically, we separate this two Hamiltonians. We apply these two Hamiltonians separately. We apply one first with some time, we apply another one with some time, right? Then you end up with some state, right?
Yes.
You measure this state, it looks like this state is far from, if you, for example, you measure the energy of the state, the energy is high, so it means there's something wrong, right?
Yes.
Then you feed back to your system classically, so I want to change these parameters, and change some parameters, and I run it again. And then I see, okay, now actually I'm in the right direction, I'm decreasing energy, I'm going to do more in this direction, and
Okay, so there's interspersed measurements,
Yes.
and then there's some dynamical length adjustment of how long you apply each of them.
Yes.
Okay.
So it's basically a mixture of quantum and classical. So we have to evolve the system quantum mechanically, but we have to do these measurements, and then classically feed back to the system and adjust these knobs to make the, calculate these cost functions. So, okay, so now hopefully I convinced you, we demonstrated these things, and you can, if you're not convinced, go back to check our papers. It's on archive. So now we demonstrated that we can use this QA/OA. We demonstrated this feasibility of these algorithms, and then can we actually use this to prepare a thermal double state? And we try to do that actually. This thermal double state has to be some entangled state between some eigenstate of two systems, right? So in this case, we choose the system to just the critical IC model, where G equals 1, where it's at a critical point. This is particularly interesting to us. At one moment we thought, we want to understand more about this quantum phase transition at finite temperature. Well, this called thermal double state. If you prepare a thermal double state, the short, if you measure part of the system, local measurements, you would see some thermal quantities, right? That's kind of a way of studying the dynamics or all the equilibrium property at the finite temperature case. So that's the motivation, and to do that, we have to reconfigure our sort of circuit more complicated, right? So so this can be done with the early version of our quantum circuit machine. We only have 7 qubits, and now we break. Since we now need two systems, right? A and B, we break this chain into two systems. The first 3 qubits in one system A, and the last 3 qubits in system B. So we initially prepare the states using EPR protocols prepare the maximally entangled state. So if you write down the state, write the state down, it looks like it's maximally entangled state between A and B, which is actually at infinite temperature. So that's you can think of the initial state as infinite temperature, somewhat double field state. But later we apply this part of the Hamiltonian, the Ising model to system A and do nothing to system B, right? And next we apply a mixed Hamiltonian between A and B, or mix A and B together. After this, we can do a state measurement and determine what's the temperature of it and how close it compared to the finite temperature thermal double state we want to prepare, right? We can measure like how far it's away. We can adjust. Then we feed back to the classical computer and adjust these knobs into different layers, or different steps, and so that we can sort of like last prepare some thermal double state. So well, the fashion of the way this works is very similar to the first thing I showed. The only difference we really have to mix the A and B state with some extra Hamiltonian here. So here I'm showing a quick snapshot of the experiment and theory. So it turned out that in this kind of optimization algorithm, we really don't need so many layers. In principle, in QAOA, the more layers you apply, the more parameters you have, the more freedoms you have, and you adjust this parameter, you can get even closer to the state you want to prepare. But it turned out that in this kind of a question, just generating the thermal double state at the grid point, the Ising model, it only takes one layer. We can get almost 100% fidelity. So basically, I'm just showing the result comparison between the theory experiment of the single particle correlator and two particle correlator. The resolution is terrible. I apologize. The blue ones is the single body correlator, basically just magnetization, right? Because we prepared as a maximum entangled state. Even in this state, it's also maximum entangled, right? If you trace one out, it's just a mixed, thermal mixed state, right? If you measure the magnetization, it's always 0. And also, we also have shown the intra-system correlator and the cross-system correlator. The intra-system correlator is the green, and the other one is orange. So step on. So what is interesting is that you can see that when the inter-system correlation increases, it means that you have a stronger coupling between your system and environment. And the entanglement actually basically distributed between the two systems, and the inter-system correlations actually decrease. So that's one of the interesting things we can do with this QAOA, with our circuit machine. With this, I hope have already give you a rough idea about.
So I'm just trying to understand. When you say that you get reasonably high fidelity with a single layer.
Yes.
If I imagine scaling this up from 6 qubits to, say, n qubits, where n gets bigger, does that mean that you're saying that your gate depth is constant, or that your gate depth grows linear?
Okay, that's a very good question. I don't know how well scale, but my expectation is that you probably need more layers. Yes, you will need it. So the whole thing is one layer. I think if you have more qubits, you probably need more layers here, and to get this close enough to the state you want to prepare.
But I guess.
Depth will scale the thermal correlation.
Yeah.
So if you want to really go close to the ground state, you need a high depth.
Yes.
But if it's short range correlated, then it's fine to do it.
You're just
Even
saying
with many
that
qubits.
you're just saying that if you have a small number of qubits, you're fine to mock up everything in short range
So
correlation.
even with 100 qubits, you can get away with like a depth 4 circuit.
Okay. Well, then I guess a follow-up question: if that's the case, then is there a reason why you guys are sticking with 6 right now?
Because it's hard to prepare. So okay, that's a very good question, and it's related to many details. But the most important thing is that in these circuit machines, right, we really need to prepare each ions and detect each ion with very high fidelity. So okay, the way we prepare that, we actually need to address each of the ions singly with a beam, right? So then put a limit how many beams you can apply from bottom from an objective. Second, that we have to detect each ion with high fidelity. So many of you probably don't know, ytterbium works at 369 and 355 nanometer. You probably don't know what that means. That means that you're working the UV, all the detection, all the electronics sucks, right? So if you put it on the camera, normally for IR, the fidelity is 90%, right? Like quantum efficiency. UV, it's 30%, 1/3 of it. So to do that, we actually need to couple each of the ions to a fiber, right? Each ion is corresponding to one fiber, and each fiber goes to a PMT, it's photon multiplier, so that we can get a 99% detection fidelity. So imagine that you want to scale it up, then you have to integrate many fibers and many beams to address that. So that's that's sort of like a scaling issue, technical scaling issue.
And having many fibers is the main difficulty is to use.
There are also crosstalks. You have to keep these ions relatively stable to the fiber tips, and you want to also have a good coupling between fiber and ions.
So the number of atoms that you have is much larger than the number of fibers that you can couple to?
Oh yes,
yes.
Yes.
So that means that the reason that you have many atoms, sorry, this is naive, but the point of working with more atoms than fibers is that in some cases you're not interested in reading things out in the middle. Just
so actually, that's okay. See, in reality, when we work with these things, we can trap more ions, but we don't really trap that much ions. First of all, because like I said, longer ion chain would have a shorter lifetime because the background collision. If you have a hydrogen collide with any of the ions, it would destroy the whole chain. So normally when we do experiment, actually, if we need 6 ions, we only load 6 ions. But in principle, we can load more. But another fact is that we only have, for example, 6 channels of fibers. Right? We only just need these 6 ions. So in a new generation machine, the Eureka machine, we can do more. We can have a bunch of fibers. We have 21 ions. We can detect all of them.
But there would be applications where you have more atoms that are
yes,
useful
if
than
you,
fibers.
Okay, good question. So if you're interested in something, you should say, I'm interested in some system that is actually pretty big, but I'm only interested in merit partially, right? Local merits. Yes, that's possible, but you also would need to apply more addressing beams to the ions as well.
You guys can also take just straight images of like 100 ions, right? It's just not as good fidelity, right?
Yes, in the system we do that. We have a 2 system where we can filter mirrors so that the light goes into the PMT or the light goes to the camera. So we can do camera, but like I said, the typical CCD, the Android camera only have 30% quantum efficiency, so you don't have very good detection fidelity. No.
So it's essentially a construction barrier.
Yes, technical details. Like I said, Chris. Said we're promising quantum computers, but we're only limited by technical details. All right. With that, I want to switch gear a little bit more to talk about more recent work on.
I feel bad because I've been asking a lot of the questions, but
but
because of the schedule, we have about 5 minutes.
Oh, so many minutes. Okay. All right, just give me a rough idea. So basically what we're trying to maybe here is try to study some confinement aspect in high energy physics in our spin system. So basically what I learned is that quarks is very hard to detect as a single particle in high energy physics because they have strong interaction with each other and normally they clump into hadrons. And the nuclear force that binds them together is mostly constant. So basically, the confinement potential linearly goes linear as a separation of the quarks. And there's one particular kind of a hadron that it's only consists of one quark and one anti-quark, and the interaction occurs linearly as a separation. So we sort of can observe similar effect in our system as well, but here we have to the particle is not quark and anti-quark anymore, but instead the domain walls here. So we have a spin system, some spin pointing out, some spin pointing down, and there this patch with the spin pointing down is one domain, and another patch is another domain. There's a wall between them, sort of like a domain wall particle, right? These domain walls can in some circumstance, some parameter space, we can actually bond them into meson-like particles, quasi-particles. So, so basically, there's some source experiments. So you start with some, let's start with some easier Hamiltonians with only nearest neighbor interactions. You initialize with some along some z direction, for example, spins up, right? This is actually the ground state of this part of the Hamiltonian if b equals 0. So if you just apply this, nothing really happens. The eigenstates just go sort of phase flip. But if you quench on b as well, what you see is that there's some kind of excitation happens where normally it appears in pairs with these domain walls as domain walls, and normally if you have some transverse field, the transverse field just try to flip your spin. As a result, these spin waves would propagate into opposite directions. You have this light cone physics, which is studied a long time ago and it has been demonstrated. So I'm going to just gloss over these things. I don't have much time. But what important is that in the experiment you can observe these two-body correlators. So you can actually see the correlation of the information actually propagates out, right? So in the confinement case, I just go directly to our case and speak to some other proposals. In our case, instead of doing just nearest neighbor interactions, right? We add in long-range interactions. So what's the consequence of long-range interaction? So at alpha equals infinite, basically it's nearest neighbor interaction. It's very similar, but if you go to the regime which alpha is finite, you have nearest neighbor interaction, next nearest neighbor, second nearest neighbor interactions. So what does this interaction actually mean? Well, it means that when these domain walls propagate out, you will have more anti-parallel pairs. These anti-parallel pairs increase dramatically as the domains actually separates. As it separates, the increase as a result, you actually as these pairs increase, you would increase the energy of the system. So that looks like you have some confinement, right? As it goes out, you increase energy, so you don't want to actually do that. So, but as opposed to a linear kind of confinement, in our system, the confinement is more like non-linear case. The confinement potential is pretty narrow here, as goes out they converge to I think is a parallel case. So as you can see, as the alpha becomes smaller, it means that you have longer interactions. The confinement is actually stronger, right? So our theorist collaborator has already demonstrated this in their numerical simulations with I believe 19 ions, where when you have like alpha equals 0 or alpha equals infinite, which is basically nearest neighbor coupling, you have this fast spreading of information, while in the other case, information was confined. You only see local oscillations. So to be more quantitative, you can just look at how fast this thing oscillates, local spins oscillates. With the Fourier transform, you can actually extract the different mass for different bound states. Here we just define the mass as the energy of these oscillations. Conventionally we set c equals 0, c equals 1. So in the experiment, we can sort of observe similar thing as well. So we can initialize the spin like this and just do a quench. This is all oscillations, no information spread at all for this long-range interaction of 1.1. We can also prepare it in a slightly higher bond state, right? You see there's these domain walls here, but they're further separated. They're more separated, so they're slightly higher energy state, but they're still bonded, right? So when they're bonded, there's no separation or no spreading of the information. And we can also do some comparison between experiment and theories. It works very well. Same thing. We can also measure the local spin flip and extract the mass of the Mason-like quantum particles, and then we can sort of like initialize to different bond state and quench a little bit, so it's also couples to slightly higher energy state. From these oscillations, we can extract the mass ratio, the mass difference between different bond state. And we compare it with experimental theory, and it works pretty well. So that's basically all. And for the last, I want to show you, we have these machines. We're open to new ideas. And all the theorists invite you to talk to us and give us ideas what we can do. For the last, I want to show you the whole group, the Chris group. There are a lot of names here, but a lot of them in the gray have already left the group, and the blue ones are still there. I'm trying to make things work. With that, I would thank you for your attention. Thank you very much.